our public education, outreaches and improvement, pollution prevention, and of course, stormwater management. The biggest question that I had is like, Dennis, it doesn't rain in California. So what do you mean? Why should I harvest water when it doesn't rain? So this one I pulled was from a weather station in Merced, and we got 12.59 inches last year as of January 2021. So what that means is with the average roof size, if you were harvesting, and you had about 600 square feet, that you could have got over 7,554 gallons of water that you could have just harvested and hoarded for yourself. Your rain garden will be able to infiltrate over 30,000 gallons per year, even with a small setup. One of the things that has to be done is we have to look at what's required for MS4. And typically, they like to work with, what you saying? They'd like to work partnership with existing programs that are already working on a solution. Not only that, they want to look at a way where we are increasing diversity, where everyone feels a bit of inclusion. Matter of fact, it's not even inclusion, it's ownership. I'm gonna move on a little bit. Now, the benefits of harvesting rainwater the benefits of having a rain garden is that it's the most simplest form of bioswale. I've worked with kids, and they're awesome because they're cheap labor, and they do a good job. But the rain garden, it recharges groundwater, it conserves water, it protects our lakes, ponds, coastal waters, and drinking water. It increases beneficial insects that eliminate pests. It also can increase the value of your home. And I stuck a little website there from the city of Berkeley, info that you can pull up, and it'll show you from like, I think it's 1650 to about 2050, where home values are increased for folks that are more green conscious. Anyway, it reduces mosquitoes, and it naturally filters up to 30,000 gallons per 1 inch rain event. One of the things I was able to, or I had to do, because I got interested in how plants took up the contaminants out of the water, is I joined the Master Gardeners, and it was pretty cool. So that helped me really get an appreciation for our public education, outreach, and improvement. Well, we're looking at rain garden workshops, planning and design, site selection, size, shape, and slope, plant selection, and maintenance. The picture you see there is from UC Merced's, it was the fair, the county fair. So we were able to do a water harvesting demonstration there. We got second place and most beautiful show. Pretty cool. Now, what is a rain garden? Well, first of all, let's look at something real quick here. We can see what happens when you don't have one. And there's tricks that you can use, like curb cuts, but you have to check with the county. Sometimes, take it from experience, you can kind of get in a little bit of trouble by doing it yourself. I've done it. But it makes a significant difference on the amount of pooling that you see in your yard. Okay, what is a rain garden? Think of it as a sponge, right? And what that sponge does is it slows that water down, and it removes contaminants that exist within that flow stream. Let's go ahead and move on past this. Harvesting rainwater. Well, the good news is that most roofing materials are totally suitable for harvesting rainwater. Metal and like the plastic sheathing that you see on like your just the greenhouses are really the most efficient for harvesting rainwater. Harvesters should be aware of wood shingles because they tend to mold, where if you're rich enough to have a copper roof, which are beautiful, by the way, but when they patina, they create different types of sulfites that are dangerous for yourself and the pets. And the 6 most common roof types are tin, asphalt, shingles, clay tiles, ceramic, cement, and rubber. Remember that each one of your rain barrels should be food grade. They should be about 6 inches away from your house. And one thing I didn't mention is that you're gonna need a lot of planting. Gotcha. Okay, what are the benefits of having a rain garden? Well, reduces stress on municipal systems, conserves water, restores the hydrologic cycle. There's a lot of good stuff that happens, and most importantly, it recharges our groundwater. You have any questions? Oh, and if we have time, I'd like you to come up and be my cloud and play with the rain barrel.
Do we have any questions?
Come on. But it comes with a flexible force. I was a bit tricky. So you're going to be my pilot. Go ahead. I drawed you in. Oh, yeah. College. Little fluid dynamics and fluid mechanics. Take off was really employing Darcy's law. Reynolds number from the mechanics. I don't want to hold you guys up anymore, but if you guys would like to come and play with this.
There you go. So I have a rain barrel in my backyard, and in this environment, it fills up really quickly.
Yes.
And then so what strategies would you advocate for to using that water effectively in the environment that we live in, that we only get water every 6-8 weeks?
Got you. How big is your rain barrel?
Just a standard size rain barrel.
55?
55, probably.
You know what I would do? I would do either a rock line swell to help move that water to a different area where I would want it to go, or I'd do a vegetated swell to allow a little bit of infiltration. If you want to go have a bit of fun, you can build a rain garden, or you could do a percolation pit. Again, we're just moving that water where we want, and we're trying to get the most benefits out of it. Most important thing is to allow it to get in the ground. And before you do your percolation pit, always call 811 to make sure you're not hitting the line.
Sounds great.
Yeah.
Thanks.
Thank you. All right. Next, we have Kyle Leathers, and he just did our demo earlier. He's going to be speaking on current and future thermal vulnerability in the Sierra Nevada streams.
Okay. Thanks, everyone, for sticking around till the end. We're almost done. But I'm going to share some results from my PhD so far at UC Berkeley. And I'm currently living in Davis, which is pretty close by to Sacramento here. I happened to visit the State Fair, where at the end of the night, the band Smash Mouth played. And their hit song, All Star, they happened to make a climate prediction that I'm not sure has been tested yet. And we can break down their prediction of the water getting warm, so you might as well swim, into two different parts. Is freshwater getting warmer, and is it safe for organisms to swim in? There's some reason to believe that freshwater could be getting warmer here in the Sierra Nevada. It's predicted by the end of the century that air temperatures could increase by 3 to 6 degrees Celsius by the end of the century. And this might reduce the amount of snowpack, resulting in more years like 2015, which was a severe drought year, being the norm by the end of the century. This could also result in earlier snow melt and an earlier period of low flow. So in addition to higher air temperatures directly increasing water temperature from long-wave radiation, we could also see low flows indirectly increase water temperature. Low flows can result in reduced thermal buffering for streams. They can also result in increased residence time as water velocity declines, so the water has more time to heat up as it travels the same distance downstream. And if low flows are occurring earlier in the year, then we could see a higher overlap between the period of base flow in California and the Sierra Nevadas and the period of peak air temperature, which will also increase as a result of climate change. So this supports that the water might be getting warmer, but does it matter for the species that are there? Well, for some macroinvertebrates, which are important for a lot of ecological processes, there's variability in how sensitive they might be. We generally think of Ephemeroptera, Plecoptera, and Trichoptera, or EPT, as being more sensitive, and some other taxa, like chironomids that might have hemoglobin to survive in high temperatures and low dissolved oxygen, being more tolerant. One way we can test how sensitive they could be to warming temperatures is to look at where we find them. One thermal threshold that's been discussed in the Western US is the CD75 value, which is the thermal temperature at which 75% of occurrences have been found for this species. So it's likely that they're stressed at higher temperatures. And these temperature thresholds vary a lot by macroinvertebrates we commonly find in the Sierra Nevada, with some Plecoptera like Dorinuria even being potentially sensitive or only found at temperatures around 13 degrees Celsius. So there is reason to believe that water temperatures might increase, and some species can be pretty sensitive at low temperatures. And that leaves us with the question whether Sierra Nevada stream communities are vulnerable to warming from climate change. I'm attempting to answer this by breaking down vulnerability into two different components of exposure, which is the thermal environment that a species experiences, and the sensitivity of a species, which is how it responds to its thermal environment that it experiences. We can break down exposure further into when is vulnerability occurring, how does water temperature respond to air temperature over time, over temporal scales. We can think about where vulnerability occurs, at what spatial scale is variation in water temperature happening, and then why might there be that variation in water temperature to get at the mechanisms over space and time and try to predict current and future climate change or thermal distributions in watersheds. One way we can think about the temporal scale is the thermal sensitivity, or how water temperature responds to air temperature. In some streams that are spring creeks and primarily fed by groundwater, there might be no response at all from water temperature to changes in air temperature throughout the year. Alternatively, there could be a constant rate of thermal sensitivity in a shallow creek that's exposed to the sunlight directly, and it might have the same rate of change in response to air temperature. However, it gets a little more complicated when you add something like snowpack in, as an increase in air temperature could actually cause snowmelt and cold water to flow into the stream. So it's more hard to predict what might happen over time. In the same way, there could be alternatives to the spatial scale of variation within a watershed. There could be no variation among a watershed where water temperature fluctuates in roughly the same way. There could be variation at the reach scale of about 50 to 100 meters, where it responds similarly over that scale, but not at larger scales. Or there could be microhabitat variation, where every pool or riffle microhabitat has its own unique way that water temperature varies over time. If we're able to answer the spatiotemporal scale questions, then we can combine that with spatial stream network models to predict the current distribution of thermal habitat in a watershed. And we can plot that over a range of experienced temperatures. So in this example, we can see the gray star representing 50% of the watershed has a maximum temperature lower than 15 degrees Celsius, or the thermal habitat at 15 degrees Celsius at 50% of the watershed. If we use our thermal sensitivity values that we find earlier from temporal scales, and we combine that with future predictions for air temperature increasing, then we can predict the future distribution of thermal habitat in a watershed. And we might see a decline in the availability of cold water habitat so that only 25% of the watershed has water temperatures lower than 15 degrees Celsius. Similarly, we could look at the distribution of sensitivity or stressed organisms over a range of temperatures. Using those CD75 values, we might be able to say that at 15 degrees Celsius, 40% of the taxa in a community are stressed out. And if we combine these two distributions, then we can start to answer vulnerability. If the percentage of available habitat in red is higher than or roughly equal to the percentage of taxa that are stressed at a certain temperature, then the community is likely resistant, like the top right graph. However, if the percentage of taxa in a watershed that are stressed at a certain temperature is higher than the percent of habitat available to them, then there might be a mismatch, and some taxa might be locally extirpated or extirpated entirely from the watershed. And to answer this, I went to the Bull Creek watershed in Sierra National Forest, and we used a nested spatial design with 60 water temperature sensors recording at 15-minute intervals. And we had reaches varying from headwaters that might have only been a foot wide in some places to intermediate-sized reaches and main stem reaches that could be 15 feet wide, all in the rain-snow transition zone that's likely especially vulnerable to future climate change. These sensors were deployed in nested spatial design, so in addition to being deployed in 10 reaches spread throughout the watershed, each reach had a layout of 6 microhabitats with 3 paired pool riffles. And each water temperature sensor had a corresponding air temperature sensor that was secured on the bank. Out of the 60 temperature sensors we deployed, 52 were recovered without any issues from either intermittency or being swept out of the main channel from floods, and they were used in time series models to answer our spatial and temporal questions. First, looking at the variation over time for our study period of 2020 to 2021, which was a mild drought year in California, we first saw that air temperature didn't vary much at all among the reaches in our watersheds. However, water temperature varied substantially more, especially for the headwaters, which had the highest water temperatures and the lowest water temperatures at the same time. This is likely because the main stems have a higher volume of water and more thermal buffering that slows down their rate of change in different reaches. If we look at thermal sensitivity, which you can interpret the y-axis here as the change in water temperature per 1 degree Celsius increase in air temperature, then we see that thermal sensitivity is positive throughout the experiment for essentially all of our reaches, which supports that increases in air temperature going forward likely will increase water temperature in turn. We see peak thermal sensitivity from late spring to early fall, with peaks in the spring, possibly in the headwaters, being due to some reaches being covered by snow and increases in air temperature melting that snow and exposing it to atmospheric warming, which was a little bit unexpected for our study. However, since we saw a positive and pretty close to peak thermal sensitivity during July and August, which is the period of highest thermal stress in our system, it supports that this period likely will be impacted going forward in the future. To focus on that period a little bit more, when the highest maximum water temperatures are experienced, we can see the variation among our reaches on average in max water temperature. And that the headwaters, again, have the highest variability, with some having peak water temperature and some having the minimum max water temperature within the watershed. Interestingly, right before the Creek Fire, there was another wildfire that caused a high amount of smoke in the area and a synchronous decline in the maximum water temperature for all of our sites, which was also a bit unexpected. Looking at the same study period of peak thermal stress, we were able to examine the spatial scales of variation using multivariate autoregressive models. And using these, we found that the watershed scale was oversimplified, the microhabitat scale was overcomplicated, but our reach scale was the Goldilocks just right scale, which supports that variation in water temperature might vary at 50 meters to 100 meters and should be considered for thermal refugia or for monitoring if you're trying to understand all of the variation within a watershed. And it would be overkill or unnecessary to sample every pool or riffle habitat in a watershed, but it might be overgeneralizing to say that water temperature is the same over a kilometer, like some models might do. So with this data, we've seen that there's some spatial variation going on. So why is it occurring? We can use a spatial stream network model to try to get at some of these drivers, both abiotic drivers and spatial autocorrelation. And when we did that using the white halo circles of our observed values for maximum water temperature, we found that elevation, discharge, and conductivity were the main abiotic drivers, possibly related to higher snowpack at higher elevations, our conductivity being related to shallow snowmelt influence, and higher discharge being related to increased thermal buffering. However, upstream water temperature was the primary explanatory variable and explained about 70% of our variation in maximum water temperature in our best model. So thermal vulnerability has the potential to propagate downstream. And it might not be very effective to do local reach restoration efforts if the main problem is still occurring upstream for what's going into the channel. We were able to use our best supported spatial stream network model and use universal Kriging to predict maximum water temperatures throughout the watershed, which you can see as the streamlines. And that agreed fairly well with our observed values and supports its use in potentially predicting future water temperature. We used our observed thermal sensitivity value that we got using multivariate dynamic linear models from before, looking at when variation occurs. And we combined that with downscaled global climate model predictions of air temperature increasing by about 5 degrees Celsius by the end of the century here, to predict that water temperature could increase by 1.5 degrees Celsius throughout the watershed by the end of the century. This could result in a 25% decline in cold water habitat of 15 degrees Celsius, which might have implications for the species that we find there. To test whether that is occurring, we can look at our distribution of stressed taxa within the community based on long-term data from Dave Herbst from about 10 years of him collecting data in Bull Creek. We can see that the EPT taxa in green are indeed stressed at a higher percentage at most temperatures compared to the community at large. But when we overlay the percent of available habitat at these temperatures, we see that it matches pretty well with the EPT taxa, and there's even an overabundance of cooler habitat for the community at large right now, based on our thermal distributions. However, with our end of the century predictions, we see that there's a potential for a mismatch, where there could be a decline of about 26% of the EPT taxa and the community at large in current cold water habitat at 15 degrees Celsius, if nothing is done with climate change, and potentially even the extirpation from the entire watershed from some taxa that are extremely sensitive. But based on these results, we can conclude that increased air temperatures might increase water temperature by the end of the century, as expected to do so. That thermal vulnerability tends to vary at the reach scale, about 50 meters. Elevation, discharge, and snowmelt were our main abiotic drivers. However, local upstream water temperature was the best predictor of what's happening downstream. And sensitive taxa are indeed vulnerable to future warming in the Sierras. And this partially supports Smashmouth predictions that freshwaters are increasing in their water temperature, but it's not safe to swim for many organisms that are there. With that, I'd love to answer any questions you have and talk afterwards.
So I've been arguing with my hydrology colleagues for at least 20 years regarding the role of air temperature versus long wave radiation as the driver of stream temperature, and they argue that air temperature is a very minor component, that the exchange of heat between air and water is very small. If you thought about using long-term radiation instead of air temperature, would your predictions be any different?
When you say, or would the main measurement for long wave radiation be direct heating in some way? I'm not sure if the sensors would be the same for how easy it would be to replicate it across the scales, but it would probably get more directly at the driver because air temperature is mainly correlated with the long wave radiation.
Right.
But I think it would be more impactful for the smaller streams, and you might not pick up the impact as well for the larger reaches.
So currently, groundwater comes out at about mean annual air temperature. But over time, groundwater will adjust to increase regional heating, right? So over time, groundwater temperatures are going to increase as well. Did you try to incorporate that change in groundwater temperatures in your future projections?
Yeah, the groundwater is very complicated in the watershed based on some work that Safik Khan has done in UC Merced. And based on working with him in some past papers, it supported that a lot of the groundwater influence at higher elevations in the headwaters is due to shallow snowmelt rather than deep groundwater, where I think it would be more impacted by the local temperature to ground temperature. So I think the shallow snowmelt associated with really low conductivities that we saw in the coldest sites is likely less affected by air temperature if it's traveling a short distance and if it just melted. But the farther away you get from the snowmelt period or the deeper the groundwater is coming from, then the more it could change, if I'd think about it.
So this is clearly something dear to my heart, so I'll just ask one more question and then pass the mic. Some of the modeling we've done in the past suggests that for especially really high elevation streams, that with climate change, we'll actually see an increase in invertebrate biodiversity rather than a decrease, and that seems to be because most of the taxa at really high elevation are actually below they're in environments that are below their thermal max, and so as we heat up systems, more taxa will be closer to the thermal max than are their thermal optima. Does that play any sort of role in your predictions?
Yeah, we didn't include species that might migrate into the watershed, but that has been observed in other studies where it's not just a loss necessarily, but some species will benefit from it as well and do better. And yeah, so I think unless you're very on the low threshold for the water temperature you can handle, then you might benefit or not be affected, or at least you might be able to move upstream a little bit. But it's probably the very cold water adapted, like glacial melt chironomids that have the highest chance of total extirpation.
And of course, all these models presume that these things can get anywhere instantaneously. And so if we incorporate dispersal constraints, what's the picture look like?
Yeah, I think a lot of the macroinvertebrates in the Sierras don't necessarily have the best dispersal, so it'll be taxa dependent for how well they'll do. For some clumsy flyers or flyers that aren't going to live very long, only a day, it might be harder for them to make it from over a range if the entire watershed runs out of suitable habitat that they're in.
Nice work.
Thanks.
Hi, so I thought that was really interesting, and I really appreciate hearing your discussion with Chuck. But one thing I've been trying to do is see if we can infer something about thermal stress on stream organisms, on stream communities by looking at the type of taxa we have present and whether we have sensitive taxa or whatnot. Do you think? I guess I have a two-part question. Do you think that is likely to succeed, and do you think that we're going to have equal success in trying to do that in an area like the High Sierras? It's very cold versus low elevation coastal California. Will it be as easy to look at thermal impacts in both types of settings?
Yeah, I think that's a good question. And I think the Sierras are a little bit unique, and they tend to have less degradation and additional anthropogenic stressors. So I think it's easier to ask some of these questions about climate change there because you don't have other competing stressors that could have an impact as well. And because it's potentially a greater range in temperature, and you have more potential to see that. So if there's an equal large range in water temperatures in another area in California, if the Northwest or the coastal range, I think it could still be effective, but it's likely that species aren't just affected by water temperature, with other things going on. And with low flows, you have reduced water velocity, which might matter for filter feeders, or increased sedimentation, which might matter if you need a certain substrate to survive. That's probably a combination of factors to be concerned about in addition to water temperature.
So how do we go about looking at climate change impacts in warmer Mediterranean California?
Yeah, I mean, a lot of the taxa, if it's already in an intermittent environment, then it might be fairly adapted to harsh conditions in that instance already to some extent. And then seeing, I guess to some extent, if you have heating in some areas more so than others, if there's a difference that you see right now in the community that results, and if so, then you could start to have some implications for in the future if it does heat up like this other area that's already heated from wastewater or heating upstream in some way or altered conditions, then you can expect it.
I was just curious if you compared your results to any of the other predictions that are out there, such as the Norwest modeling, and what different scales of modeling.
Yeah, so Norwest is at a much coarser scale. I mean, it takes on a huge area, so it's has a bigger task it's trying to take on in the first place. But they're modeling water temperature being really similar over like a kilometer distance compared to a lot of variation occurs within. Like our watershed is only about 1.5, 2 kilometers in total length, but you see variation from 12 degrees or like 10 degrees maximum temperature to 20 degrees maximum temperature. There's a lot of variation in potential thermal refugia that you might miss if you generalize over the larger scale.
Thanks.
Any other questions? Thank you.
Thanks.
All right, up next, we have Mark Selos for Under Budget Quantifying Reservoir Greenhouse Gas Emissions in Pursuit of Net Zero.
Kind of works. Hey, yeah, thanks for having me, and thanks to Shuka and everyone who played a part in organizing this meeting. I've been a few years in a row now. It's always great. And yeah, so I'm Mark Selos. I work with Valley Water, which is the Silicon Valley's primary water management agency. And we're kind of unique in that we handle not only wholesale water supply, but also flood control and environmental stewardship. And we actually own and operate 10 reservoirs that are in Santa Clara County. And today I'm going to talk about what CALs and reservoirs have in common and why we need to be considering both in our global carbon budgets. And so by now you've probably seen that a lot of different companies have made commitments to achieve net zero or carbon neutrality. And surprisingly, in some industries, over 50% of companies have made these pledges. And thankfully, a lot of water agencies, especially in California, have followed suit. And so this is just a small collection of the many water agencies that have made pledges for carbon neutrality in the next 30 years. And I'm going to go in today about how reservoirs play a part in that and how we should really be considering them in our carbon budgets. And so I don't really probably need to go over this to many of you, but the thing that I wanted to point out and just remind people about greenhouse gases is that they're not all created equal. And so we have carbon dioxide, which is kind of the poster child for greenhouse gases in our atmosphere. But then we have a lot of other greenhouse gases. The two main ones that we think about are methane and nitrous oxide. And methane is 25 times as effective at trapping outgoing thermal infrared radiation as CO2. And so we think about and we talk about methane as having basically 25 CO2 equivalents. And so if you hear me say CO2 equivalents today, that's what I mean by that. And then nitrous oxide is really, really a powerful greenhouse gas, and that's about 300 times as strong as CO2. And so I think that we're all pretty used to thinking about greenhouse gases coming from anthropogenic sources, and a large portion of them definitely do from things like fossil fuel combustion and industry and forest fires. But we also have a lot of CO2 and other greenhouse gases released from natural sources. And so at night, we know that plants can respire. I'm respiring right now and releasing CO2 into the atmosphere, sorry. And we can also have CO2 and other greenhouse gases being emitted from volcanoes. But by and large, the greatest producers of greenhouse gases, naturally, are bacteria and other microbes. And with our modification of these natural hydrological systems by dam creation, we can expedite those processes to the extent that it's kind of hard to say whether they're natural or anthropogenic. And so we're probably all most familiar with aerobic bacteria, which basically use oxygen as an oxidizing agent to break down carbon, and they release water and carbon dioxide. But when oxygen isn't present, a bunch of other microbes can take over, and they use weaker oxidizing agents to break down organic matter. And so first, after all the oxygen is consumed, we often see denitrifying bacteria become active, and those break down carbon with nitrate, and they release N2 gas, which is inert, and CO2. But in an incomplete reaction, they can also release N2O, which, like I said, is a really strong greenhouse gas. And then at really, really low redox potentials, we can have methanogens become active, and those are releasing both methane and CO2, which can have a huge impact on our carbon budget. And so I'll kind of go over how greenhouse gases are produced in reservoirs and the potential emissions pathways and ways that we can go about quantifying that. So in the summer, and actually all throughout the year, but predominantly in the summer, we have a lot of radiation coming down onto our reservoir surfaces. And since water is a really poor conductor of heat, it causes the reservoirs to separate into two distinctive density layers, where the epilimnion is warmer and less dense, and it floats on top of the hypolimnion at the bottom, which is cold and dense. And basically what happens is when lakes are stratified, there's not really exchange of water between the top and the bottom waters. And so under stratified conditions, the hypolimnion, the bottom, is essentially cut off from all oxygen inputs from the atmosphere and from photosynthetic organisms that live a lot of the time in the thermocline in the middle. And so over time, all of that oxygen in the bottom waters is completely depleted by aerobic bacteria. And they release CO2. And then after all the oxygen is consumed, we go through our microbial redox ladder, where first we have denitrifying bacteria producing CO2, sometimes N2O. And then we have methanogens that produce both CO2 and methane. And so these gases are accumulated in the bottom sediments of the reservoir and also into the bottom water. And so there are a couple of different emissions pathways for all those accumulated gases to be released into the atmosphere. The first one are diffusive fluxes. And so that basically happens when water becomes oversaturated with a certain gas and it slowly diffuses out and into the atmosphere. We also have ebullition, or we can just call it bubbling for this presentation. And it's a very jargony word. And so that happens when you get gas buildup in the bottom of the sediments to the extent that the cohesion and weight of the sediment can't keep them down any longer, and then you have these bubble plumes that form. And then also with the reservoirs, you can have turbulent degassing at the reservoir outlets. So when we're releasing water into the creek, there's a lot of turbulence, and that's causing degassing of the accumulated gases. And so we know that reservoirs are sources of greenhouse gases to the atmosphere, but the global impact is really uncertain. So there have been a variety of different studies that have attempted to quantify this. And we have a huge variability in terms of the total contribution of lakes and reservoirs, from about 750 to 3,500 teragrams of CO2 equivalents per year. And that could be about 1.5 to 6.5% of the total anthropogenic greenhouse gas emissions, which sounds kind of small, right? But for a water management agency like my agency, when we're trying to achieve carbon neutrality, those can be a really, really significant source of our carbon budget, especially in places like California where we're so dependent on reservoirs. And so we have a climate change action plan at Valley Water, And we have a whole team that went through and quantified all of our emissions from all of our operations and all of our facilities. And they came up with an estimate that we emit about 22,000 megagrams per year of CO2 equivalents. And that's not including reservoirs, emissions from reservoir surfaces. But just using literature values for Mediterranean reservoirs, we would get about that much from just our reservoirs alone. And so this basically doubles our carbon footprint. And those are all things that we have to think about when we're trying to offset. And so our question, these literature values basically aren't accurate enough to determine our carbon footprint, because every drop or every mole of gas counts when in our carbon budgets. And so ideally we would just have good Mediterranean aerial emissions rates that we could cite and use as estimates. But in the literature, those rates vary by a factor of 10. And so it's really clear that we need focused studies in each system to adequately quantify greenhouse gas emissions. And it's really a tall order to do, because it's not like we can just, put a sensor at our outlet. It's not just like measuring temperature. There are all these different emissions pathways and all of these sources of variability that we need to contend with. And so for sources of variability, we obviously have the seasonal variability, where we see in particular methane emissions increase a lot during the summer. We have these nighttime, daytime variabilities that aren't often considered in these global models. We have spatial variability, so depending on where you are in the reservoir and the local conditions in that area, you can have order of magnitude difference of greenhouse gas emissions. And then we have these major biogeochemical differences, so differences in sediment chemistry, differences in water chemistry, differences in the microbial community that we all need to take into consideration. And then on top of that, we have different types of emissions, right? Like I mentioned earlier, we have bubbling, we have diffusion, we have turbulent degassing, and then even sometimes we have plant-mediated transport in reservoirs that have a lot of wetlands attached to them. And so our challenge here is to conduct a study where we can basically quantify all of these types of variability and all the emissions pathways to generate a scalable estimate to apply to all of our reservoirs. And so to do that, we actually partnered with UC Davis, and I have Professor Alex Forrest here. He's going to be presenting after me on more of the science and the results of the study so far. But our study objective was really simple. It was to generate an estimate of total per year greenhouse gas emissions for all of our reservoirs, so we can incorporate that into our climate change action plan. And the key thing that we wanted to think about is making sure that our results are scalable. And so we manage 10 different reservoirs, and we're also tied into the state and Central Valley projects. And so we want to make sure that we're selecting a subset, a representative sample of reservoirs, that we can capture all the different emissions types, the sources of variability, and the driving variables, so that we can use that small subset of reservoirs to scale up. And so I'll kind of just go over all of those different aspects that we're trying to capture in our current studies. So for different emission types from our reservoirs, we think that those are the diffusive fluxes, the bubble fluxes, and the combination of that is the total flux. And so to measure diffusive greenhouse gas fluxes, we're having students go out into a boat in the reservoir, anchor down, and then they have these 3 chambers right here. You can see A, B, and C. And we have an automated greenhouse gas analyzer that does both methane and CO2. And they're collecting measurements of that on a fixed time scale. And we're basically generating these regressions where we're measuring the concentration in the chambers over time and fitting a regression to that, and the coefficient of the slope is going to be giving the flux. But then we know that these diffusive fluxes can vary spatially, and we can also have these bubble fluxes. So in order to quantify the ebullition or the bubbling events, we're using hydroacoustic techniques to map out all the different bubble plumes throughout the year, which can change obviously. And we're using really high resolution samplers to basically do the same thing as the diffusive flux measurements, but we're able to capture these little jumps that we can attribute to these bubble events. And then in the next year, we're planning on installing an eddy covariance tower in our reservoir, in one of our reservoirs. And that's going to theoretically give the total flux off of the water surface. And so that's going to be able to help us better quantify our ebullition versus our diffusive fluxes. So next, we're moving on to making sure that we're capturing different sources of variability. And so, like I said earlier, there are a lot of different factors that can influence greenhouse gas production and emission from reservoirs. And in order to make sure that we are capturing all of those, we've selected 4 really diverse reservoirs in 3 different watersheds. So these have different sizes, different management strategies, different sediment chemistry, different size watersheds and residence times. And so ideally, we're going to get enough ancillary data where we're going to be able to plug into a model and see what factors are influencing greenhouse gas emission rates. And then to capture that spatial heterogeneity in the reservoirs, we're monitoring at 3 different stations in one reservoir on a quarterly basis. And we've gotten some pretty interesting results there. But yeah, we're definitely seeing differences from like the shallow areas versus the deep areas in terms of emission. And in California, since our reservoirs fluctuate so often, that can be significant. And then finally, to capture the diurnal variability, we have some very unfortunate or fortunate students who go camp out at the reservoirs on a monthly basis, and they're taking measurements throughout the day and night. And so we've seen some pretty interesting results there, especially in terms of CO2, because we know that photosynthetic organisms are most active during the day and then aren't so active at night. So seen some good, we're using that to kind of refine our estimates. And then finally, we're looking at the driving variables. And so these measurement of these driving variables is really important if we want to scale up our results to other reservoirs that we're not actually actively measuring at. So we're looking at things like sediment chemistry. So what are the concentrations of redox-sensitive compounds and elements within the sediment? Things like looking at the carbon isotope values and the DOC concentrations. And then also when we're taking our flux measurements, we're measuring water quality using sondes that are deployed at the surface and the bottom of the reservoir. And so that's helping us kind of constrain what are those drivers in the diurnal variability of emissions. We're looking at gas storage in the reservoir using hydroacoustic methods, which is going to be the main focus of Alex's talk, so I won't really go into that. And then we're also looking at meteorological variables. So are we seeing more emissions when we have high winds, when we have a more incoming radiation, stuff like that. So yeah, putting it all together, we are attempting to quantify my agency's total greenhouse gas emissions from just the sample reservoir shown circled here. And so yeah, so this study's underway. We don't have a whole lot of results yet, but you'll see some from Alex coming up. But I think it's just worth mentioning that reservoirs are significant but poorly quantified sources of greenhouse gases to the atmosphere. And if your agency has a carbon neutrality goal and manages reservoirs, you really ought to be considering them when you're trying to reach that goal. However, focused studies are needed to accurately estimate greenhouse gases from Mediterranean reservoirs because the literature values are kind of all over the place at the moment. And like I said earlier, every mole of gas counts in our budgets. So yeah, just wanted to acknowledge everyone working on the project. We have had tons of great grad students and student collaborators. Yeah, so thank you. And hopefully Alex will be able to answer some more questions, or I can take any.
Give me 1 second. I need you to speak in the mic, or else nobody online can hear you.
Would you say that, or is there any look into how phytoremediation would have an effect on your wetland portion?
Mm-hmm. So phytoremediation, it's an interesting idea because it might not be so good for greenhouse gas emissions because you can have emission of methane that's actually mediated by plants. And so it could potentially create a source. And another thing is with phytoremediation, since we're adding vegetation or adding wetlands with like high organic carbon are thought to be big contributors to carbon emissions because you can have more methanogens active. So I would say in terms of like phytoremediation for greenhouse gas control, it's probably not the strategy. However, what I showed earlier with that microbial redox ladder is that our biggest producers of the worst greenhouse gases are only active under zero oxygen conditions. And so people have thought about installing reservoir oxygenation systems to oxygenate the sediment water interface for a variety of reasons. And those could potentially be a strategy to mitigate greenhouse gas emissions from reservoirs, so long as the generation of the oxygen isn't requiring more energy than you're potentially saving. Yeah, which is maybe not the case. But that's one thing that we're looking into in our study too, because in one of these reservoirs we have an oxygenation system. And so we're interested to see if that decreases the emission. Yeah.
Any other questions? Ali, are there any questions on? Thank
Cool.
you.
Thank you.
All right, our last speaker of the day, Alexander Forrest, is going to cover hydroacoustic sensing of methane storage in California reservoirs.
All right, for the last people in the room. Thank you. So Mark did a great introduction to the topic that we're working on, looking at methane storage and methane generation in lakes and reservoirs in California. This started as a collaboration coming out of COVID. We actually had a collaboration in Spain that when our international travel shut down, we were desperately started looking for a partner. And so Valley Water was kind enough to let us start studying their system. And then we've developed a great relationship since then. So this has really been a good partnership between Valley Water and UC Davis. I also, part of one of the hats I wear is also through the Tahoe Environmental Research Center. So that's where some of this research is based. So I'm here today representing my PhD student, Ruth Thurkel, who's actually in Spain at the moment using one of these techniques to inspect lakes, high methane producing lakes around Granada. So the story will go on. And there's a whole, like Mark mentioned, there's a whole host of characters involved with this that really make it possible for me to be standing here. So Mark did a great introduction to the methane problem, but I'll add some more slides. And so we know methane is increasing. So on the left here, the laser pointer doesn't, you can kind of see it. So the methane production is increasing. We know it is. Up on the top, this is 2003 to 2005. We can see methane hotspots around the world that are increasing again from 2008 to 2010. We know this is a major issue. There's been some global synthesis papers based on this. And specifically, it's a problem around areas that go through big swings in hydrological regimes. So this is a similar slide to what Mark put up, where we are dealing with bubbling methane and then diffusive methane and being able to partition it between the two. Part of this, in both those mechanisms, is the methane storage that's in the sediment. And that's really what we're going to focus on here in this technique that we're using. So, but before we get there, and this just sort of touches on one of the questions that came up earlier, in terms of different regimes in different areas. So here we have rivers, lakes, through different sort of production rates. So lakes and reservoirs can be major production sites. For methane production globally, But this is not just latitude, but it's also its trophic status. So trying to understand the trophic status of the lake and potential shifts of trophic status in future climate scenarios will also affect greenhouse gas emissions. So when you talk about budgeting and we talk about net zero, we talk about net zero in the present, but then we also have to think about that for future scenarios. So we're focusing on methane, and basically because we initially wanted to look at more eutrophic systems, one of the areas that our group also looks at, although not necessarily for methane, is Clear Lake, which is a hyper-eutrophic system, and trying to rehabilitate Clear Lake. So this is an ongoing question for us in terms of trying to understand the dynamics of these systems. And methane is, in a eutrophic system, is really one of the major greenhouse gases to try to understand it. But like Mark mentioned, greenhouse gases from Mediterranean climate lakes and reservoirs are pretty poorly understood. This is a synthesis paper of methane ebullition around the world, and looking at various drivers. And so, for example, this middle panel here, you can't really see it highlighted in red, but this one is sort of one of the major drivers, is ebullition versus surface sediment temperature. So as lakes and water bodies heat up, that's going to heat up the sediment, which is going to drive more anaerobic respiration and drive more methane flux. But this synthesis paper was really based heavily on temperate lakes around the world, which is not what we have or what our colleagues have in Spain. So this is really where the focus started. And so then the other question is drivers. So this is another synthesis paper by Diemer et al., looking at drivers of methane versus area, latitude, depth, DOC, chlorophyll. And chlorophyll is really the one, I wouldn't say it's a smoking gun in terms of production rates, but at least it's the one that actually has a positive relationship. And so as your lake dynamics change, as the productivity of your systems change, that's going to drive more chlorophyll production, which will subsequently drive methane generation. So we partnered up, and Mark already outlined some of the work my students have been doing with gas chambers and going out and measuring flux rates. But another technique that came up was this idea of trying to go and map with hydroacoustics and map potential methane storage in the sediment. So we chose 4 sites, the same 4 sites that were mentioned earlier. We have Stevens Creek. On the left is the smallest of the 4. This is originally the one that has the HOS system, the hypolimnetic oxygenation system. I'll never say that without stuttering over it. So that system, the idea is to look at how that system impacts the stratification and the potential greenhouse gas generation. Unfortunately, because this study started 2 years ago, it approached dead pool last year, and so we've had issues turning it on reliably. So that system we haven't looked at as much. So we focused on these 3, Chesbrough, Almaden, and Uvis. This is bathymetry collected by using the sensor using the hydroacoustics that we're using. So you'll notice at the tail end of some of these reservoirs, we don't go all the way. It's because they're dry, so we can't get out there in a boat. So this is one of the big challenges that we've been facing as well. What we were trying to capture was a range of surface area, and more important, and a range in trophic status, and a range in depth. So the biggest variation that we've seen is range in depth. The trophic status is about the same across all 3. So biosonics. So we used biosonics hydroacoustics. So this is a split beam system. So it's a 70 199 kilohertz system, which we point in the water. This is it mounted on the boat. So this is a little John boat. This swivels down into the water. And then we basically just drive around all day and collect as much data as possible. Similar to if anybody's ever been involved with an ADCP survey, bathymetric survey, so basically just using a fish finder to figure out your bathymetry. we're doing the same thing, but instead of doing bathymetry, we're mapping the return off the bottom. So this is a typical profile in depth of the volume backscatter of the system. So when you get a bounce, acoustic bounce off the bottom, you'll get a peak that looks like this. And Anderson and Martinez published a paper in 2016, and an earlier one in 2013, where they basically looked at this in Lake Elsinore and came up with basically came up with a ratio of what that would look like in terms of sediment methane storage. So we applied the same technique for these lakes that we're looking at. So basically a fish finder, we transmit and then receive the signal off the bottom. Okay, so this is, as we're driving along, what you saw on that previous slide was a single profile looking down. Now imagine it in color, and then each ping through time. So basically, each time you see a discrete discrete line, it's basically, it pings 4 times a second. And then, so imagine us driving along in the boat across the top and doing these curtain plots. And so we end up getting these raw echograms, is what they're called. And the bottom, this is the bottom return across here, this bright red. So from that, we can derive the sediment bottom, or the lake bed. And then you see, if it works here, bubble plumes coming up. And so my PhD student, one of the things that she does is she'll use this as an indicator, a sort of qualitative indicator of where bubble plumes are. So she'll go through and geolocate and tag in the echograms. She'll tag where each one of these plumes are coming up to see where the bubbly flux is. Then the bottom. The other thing that we see is these sort of large, hard return blobs. You sometimes see fish that get distorted. This is most likely algae, where it's not a distinct plume coming up, so she doesn't add those. So what does this look like? And I apologize, the colors don't stand out nearly as well as they do in my own computer screen. So if anybody ever wants to look at this, please send me an email. I'm happy to provide any of this data. But the idea is that on the left, you get geolocated map, and this is no longer bathymetry, but this is the return coming off that echogram of the bottom. Then Anderson and Martinez published in their 2018 paper a relationship between the backscatter strength on the x-axis and the sediment gas volume on the y-axis. And all their data is the black dots in here. Now we've gone and added more using their same technique to this relationship. And then using that relationship, we're able to take our hard bottom return and turn that into a sediment gas volume storage. So basically the amount of methane that's there, the potential methane that's there. So part of it is being able to quantify it. You can't see here, and I like to refer to myself as color challenged rather than color blind. So I even have trouble on my own computer screen seeing red over blue. But there's these little red asterisks that are sort of here in the thalweg of the reservoir. And these are showing where Ruth has gone through and geotagged where the bubble plumes are. So we're seeing a higher density of the ebullitive flux along the thalweg, and then the edges don't have as much sediment storage there, or sediment methane storage. And so we're seeing this as we're able to, this slide is basically to show that it's not just a fluke, or it's not just a fluke of the data set, because this is in October versus February, so October on the left, February on the right. This is taken from Stevens Creek. In the October one, which is right at the tail end of our production period of methane, we see a lot of the ebullitive flux. There's a lot of red asterisks right around the center, right around where the warmer color is here at the deepest part, which is where the greatest diffusive flux is for the system. Versus the winter, when it becomes destratified and otherwise well mixed, and we no longer see the ebullitive flux, and our methane storage potential is also greatly reduced in the winter. So we do see a seasonality to it. So speaking to Mark's point about if you're trying to get to net zero, It's really, you have to think about the seasonality of the flux in a system. And then we can use this technique and start tracking all the seasons. So in addition to going out on a daily basis, we're also going out on a seasonal basis and doing whole lake sort of synoptic surveys of these lakes. So as a sort of point of reference, doing one reservoir takes us about a day to go out and survey the entire lake at once. So this is a tool that allows us to do very quick, rapid assessments of these systems and understand the storage potential therein. So one of the other part of this, or the other part of this discussion is, it is a remote sensing technique. And so everybody always says, well, how do you validate it? How do you validate your remote sensing? So this is our custom-built, expensive bucket, where basically we have a slanted gas trap inside, and this is a depressor weight. And the idea is we lower it down, the depressor weight hangs slightly below the bucket, and so the depressor weight hits just before the rest of the chamber lands on top of it. So the gas, and then we are able to figure out the amount of gas being released from the depressor weight that's then captured inside the bucket. And then up here on this side is basically a small tube, which we then connect a syringe to withdraw the gas that's trapped inside. And we can actually test it for methane. And that's how that relationship that Anderson and Martinez to convert from the acoustic return to an absolute value of sediment storage. This is a problematic system. It does periodically flip over, and then we have to drive somewhere else and sample again. But once you have the technique down, it does work fairly well as a validation tool. We're trying to build the next generation now of a sampler that will work in a more automated sense and provide more fail-safe, where it's not tipping over as much. So the other part of this, and I again apologize for the colors. So this is taken out of UVIS. And so now these plots are actually showing delta change between seasons. So this is winter to spring. And if you look very closely, there's a black line right around there, and that's where the thermocline is positioned. And as you can see, the warmer colors of so winter to spring will be more production of methane, will be a warmer color. So the warmer color here basically tracks the thermocline position almost exactly. So this also supports this idea that it's an anoxic condition that's being generated by the thermal regime, and that we're able to capture that using this hydroacoustic technique. This is spring to summer, and again, you see stronger production right around where the thermocline is. And then this one is summer to fall. Now, because we're tapering off in the production season of methane, it will come out, the greatest change will be a darker, cooler color, and again, it tracks the thermocline. So really, how it tracks the thermocline in a water body that maintains a constant water level is important. And that's an important distinction when you're thinking about lakes versus reservoirs. So reservoirs, we tend to manage them by letting the water levels swing wildly up and down, or at least in a very controlled fashion, up and down. And so this is one more plot of showing where the thermocline is. Before we get to, so as it swings up and down, we need to understand where the thermocline changes relative to the position of the bathymetry and understand the role of different zones in the lake. So this is the conceptual model that we're working with now. And so we have spring, summer, winter, fall, and basically how the regime changes in the riverine zone where that river is coming in. We started referring to the middle zone as a transitional zone where the thermocline intersects the shelf break of the reservoir. And then finally, the deep water zone or the lacustrine zone. We're moving away from using littoral and pelagic to just understand these regimes across the system. And I'm more than happy to, you can't see a lot on this slide with the colors, but I'm happy to send out this model in terms of what we're thinking to look at the different rates of ebullitive flux versus diffusive flux at different times of the year. But peak production time for methane is generally summer and fall, and then it tapers off in the winter. And this is something we need to understand going forward. So the other really interesting result that we found in terms of reservoirs is this idea of re-wetting and re-wetting a system. So this was in 2021, and this was a low water year, so 513, and where we basically had not a lot of methane generation, and that was sort of what we were expecting that year. And then in 2022, at almost the exact same time of the year, Valley Water had brought in a lot more water into their system, and the water level had gone way up. And it had re-wetted a lot of the area that hadn't been wet in a couple of years. And what we saw is a lot more methane flux basically fluxed off right away. And so this is one of the sort of very interesting sort of findings that we opportunistically asked and went after when the event happened. So in terms of thinking about reservoir management, this is something that we have to factor into operations if we're trying to think about carbon neutrality and greenhouse gas flux emissions. So, previously exposed sediments are a large source of sediment gas once they resubmerge, and it will be for a brief period of time. But this will also track along with where the thermocline is. So you have to be thinking about the thermal regime, and one of the things we've now done is we've gone through and put in a thermistor chain mooring to track where the thermocline is. So here you can, this dashed line is meant to represent the thermocline here that then moves down in the summer to here. This gives you an indicator of where the production is going to be in the system. So you have to understand the thermocline and you need to understand where your overall water level is in order to understand the final overall production. So some preliminary conclusions coming from this work. So the subset of California reservoirs displayed strong daily, high during day and low at night, and seasonal, high in summer and low in winter trends in methane production. And it's this seasonality that we're really able to capture with this hydroacoustic technique. Correlations exist between chlorophyll A and water temperature, leading to increased methane production in future climate scenarios. And then that's also, we have to be able to survey that and monitor it. And then finally, hydroacoustic techniques suggest a spatial distribution of gas storage and provide a method to capture the bubble plume formation. So to allow us to be able to partition the ebullitive flux and the diffusive flux, and looking at not just assuming that the entire field is exactly the same, and that we're able to differentiate different parts of the lake as being high production zones and low production zones. And to Mark's point of every mole counts, well, if you're counting every mole on that scale, then you have to be counting the spatial variability on this scale if you really want to do some accurate accounting. So with that, I'll leave it with our noble boat that our students take out and any questions that you may have.
I think that was really interesting. I have a couple questions. First, do you think hydroacoustic monitoring is practical to apply on a large scale? For example, if you wanted to do an assessment of all of California's lakes and reservoirs and like a probabilistic assessment. And second, what do you think is going on with the re-wetting? Is it that those are the types of habitats that are more productive, or is it actually something about it being dry and like maybe like if the water level stayed high, will they continue to be high producers?
So to the first question about the scalability, it would be very challenging to do this on large reservoirs or extremely deep reservoirs. So that's another area of my work is in Tahoe. Trying to do this technique in Tahoe doesn't work. We actually do it to track mysis shrimp. And tracking mysis shrimp, we can track down to about 60 meters using this technique. So there is a scalability of both size and depth. And to Mark's point about how do we scale across multiple reservoirs or multiple agencies, I think what we can do is come up with representative sampling. So not necessarily trying to do a whole lake, but doing subsets that are representative of both different meteorological regimes, but also different nutrient regimes, and then also within large lakes, a regime within the lake itself. So I believe there's applicability across different systems, but you'd have to be selective to make it cost effective. And then your second point is what's going on with the re-wetting. And my short answer is Mark. No. No, my short answer is we're not entirely sure what's the driving mechanism. And we're trying to understand, and that's exactly what one of my students is trying to understand now. What we did see is we actually returned shortly after that re-wetting period when it was still high, it was like 3 weeks later, to see if it was still high production. And it wasn't. So it had dropped off right away. So we think it's something to do with the re-wetting somehow triggers a release of potential stored material. And I think it has to do with as it dries, as the water level, this is just a hunch, so as the water level dries, that organic material gets dried and basically gets onto the sediment. And then as it re-wets, there's a lot of organic material there that all of a sudden becomes very active. And then once that's used up, that's gone again. So I think it's a matter of sort of settling that down through the water column and drying it out. That's my hunch. Mark?
Yeah, so I think that definitely the settling of organic material and accumulation under low pool conditions is a factor. But another thing that could be happening is that when sediments that are reduced are exposed to the air and the atmosphere, then a lot of the reduced species in the sediments get oxidized. And so the sulfide that's in the sediment will get oxidized to sulfate. The reduced metals, manganese and iron, will get oxidized to manganese and iron oxides, and so on. And same thing with nitrogen. Some reduced nitrogen can get oxidized. And so once the oxygen is quickly depleted in the sediments, once it's resubmerged, then you have all of this fuel for these anaerobic bacteria to do their thing. So you have sulfate-reducing bacteria, iron-reducing bacteria, manganese-reducing bacteria, denitrifying bacteria. They all have the oxidizing agents that they need in high concentrations to really just rapidly rip through that organic matter. So we see that with like methylmercury in reservoirs, for example. And so I think it's kind of analogous to the greenhouse gas production.
So you think there's like a lot of organic material just accumulating on the dry sediment during the dry phase or deposited from the last wet period?
Yeah, lots of organic matter accumulating, and then all of those. So like the microbial analog here would be like, say you had a bunch of CO2 in the sediment, so you don't, right? But we can't breathe CO2, right? But if it's exposed to the atmosphere, then it turns back to oxygen, and then all of a sudden we can use it. The same thing is happening with all of those reduced species that microbes use. So it basically, not only do you have the carbon, but you have all of the oxidizing agents for the microbes to use. So yeah, it's pretty dramatic though. Those bullseyes that we got were like, when we saw that for the first time, we were like, whoa, that's crazy. But,
any other questions?
Chad's got one, and I got one.
So my question is actually related to the methylmercury, like you just mentioned. Do you guys have fish tissue monitoring that you're regularly doing for mercury?
Mark just finished his PhD in methylmercury. So he can talk methylmercury all day.
Yeah, so I don't know if you were here, like I think it was like either last year or the year before, I gave a talk on hypoliminetic oxygenation for mercury control in some of the reservoirs. But yeah, so we do fish tissue monitoring in one of the reservoirs in this study, but we actually operate reservoirs that are impaired by the New Almaden mining district, so former big mercury mine. And yeah, we have probably one of the best data sets out there for mercury in fish. And we're actually seeing declines in methyl mercury right now that are persisting beyond our periods of non-operation of the oxygenation systems. And kind of sidebar, but what we think is driving that is the increase in primary productivity that basically dilutes the methyl mercury throughout the food chain. So.
So my question is, and not really knowing much about reservoir management, have you guys thought about, like I'm sitting here thinking, how do you reduce emissions from these reservoirs? Is it about like controlling levels, or where do you go from there?
That's a great question. So what do you do? Is the short question. As a reservoir manager, I don't think we have necessarily a lot of options. And so one of the options is to control our water levels. And so this idea of re-wetting the soil and fluctuating it up and down, if you have control, and Valley Water is fortunate enough to have more control over their system than, say, Shasta Dam. Shasta Dam were really sort of more at the control of weather. So we can control water level, or the other idea in terms of greenhouse gas production is looking at the anoxic condition. So basically stratification, the thermal stratification controls the oxygen regime. So if you want to maintain more oxic conditions at the bottom, then you basically have to destroy your stratification. So in order to do that, you do something like an oxygenation system or some sort of vertical mixer, which on some scales, on small reservoirs might be possible, but then on big reservoirs is absolutely ludicrous. And those are really your two control measures that are functionally possible. Mark, do you have more to add to that?
Yeah, so in addition to those, one thing you can think about is a lot of dams are now being, well, not a lot of dams are being built, but dams are being retrofitted now with the ability to withdraw water from multiple different depths. And since the methanogenesis in particular happens at really low redox potentials, so typically like beyond anoxic, right? Like really, really reducing conditions. One strategy can be to focus on bottom withdrawal. And so take that really, really reduced water at the bottom of the reservoir and discharge that downstream. It quickly gets reoxygenated, and that can potentially increase the redox potential and decrease the methane production. And then, let's see, I had another one, but I forget.
I will caveat that too, though, that gets rid of your cold pool.
Yeah, that gets rid of your cold pool. These are things that we have to grapple with for water quality in reservoir versus water quality out of the reservoir. And so, because a lot of these processes that lead to greenhouse gas production also lead to our problem stuff in the reservoir. So like manganese, iron, nutrient release, harmful algal blooms, methyl mercury, all that. It's all those reducing processes. And so you want to think about, you kind of have to weigh your priorities, right? Downstream versus in reservoir. But the current strategy that we go with is trying to preserve the cold pools and the cold releases for as long as possible. Sometimes we have to eat that in water treatment costs. So.
Does that answer your question?
Yes, thank you.
So the question is, what about nutrient management? Mark? So I'm in the civil engineering department, and so I bring a lot of the tools and techniques, and counterbalanced by Mark as a water agency person.
Yeah, so yeah, nutrient management. So like Alex showed earlier, most of the methane production happens in these eutrophic reservoirs that have really high chlorophyll. And so yeah, nutrient management, if you can reduce the loading of organic material from the water column to the bottom, that could definitely be a viable option. But so there are different nutrient management strategies, and some of them are better than others. And but that's kind of one reason why oxygenation is so appealing, because it could potentially have multiple benefits. in managing nutrients and managing greenhouse gas, along with a whole suite of other things. But yeah, there are like other methods that people have used, or like amendments that you add to the soil to sequester the phosphorus. And then another common one is flocculation, where you use alum and put it in your water column. It drops all the phosphate. But yeah, these are things that I think are definitely worth considering, not specifically for greenhouse gas control, but it would be an added benefit.
And I'll add to that two other things. So one of the things in thinking about nutrient management is thinking about internal loading of those nutrients. So oftentimes we think about TMDLs and we think about external loading, which is great. We need to be thinking about that. But then in systems where you're mixing up from the sediment, there's a lot of internal loading where that phosphorus is being sequestered onto the bottom and then reloading that back in. That's triggering these blooms of chlorophyll production or phytoplankton production. And so that's tied to it. The other part of it is actually something, Kyle, that you put up with the fire impacts. So fire impacts is a huge source of nitrogen for these systems. So we're putting in a huge amount. If we have massive wildfire smoke events, that's depositing a lot of nitrogen. That's becoming more and more well known in terms of the deposition. So it's a balance between the heating and the long wave that we were talking about earlier, triggered by wildfire events, but also being the primary productivity of the system is also being augmented by the nitrogen being put into the system at the same time. So it's not a super clear answer, but you have to factor all this in when you're thinking about all these competing variables on these systems. Any other questions? Keep checking behind me.
All right, well, thank you.
Okay, thank you.
All right, guys, so you made it to the end. Thank you so much for attending, for those participating online and in person. If you were not able to catch the contact information for our presenters, you can either just email the SWAMP email, or if you have my contact info, you can reach out to me and I can connect you with our presenters. This meeting was recorded. All the presentations yesterday and today were recorded, so I'll be planning on getting the digital files and getting them loaded online so that you can watch it again, or for those who didn't get a chance to watch. Trying to think what else. So I usually do send out a post CABW survey just to get feedback on, what we can do better. Do we need more breaks? What your experience was like watching online or in person? Do we need afternoon coffee? I'm trying to think what else. So I would really appreciate it if you do fill out that survey so that I can do better next year. And I'm trying to think if there's anything else. Presentation slides, they might be posted online, but we'll figure it out. It's just an accessibility issue.
A couple of you had requested slides, so either reach out to the speakers directly or through Shuka or myself, and we can connect you with folks for slides.
And if you do need them to be accessible, we can work with that too. So yeah, I appreciate all of our volunteers, my colleagues, Cal SFS, John, who's not here, all of our presenters, our poster presenters, everyone who else I'm missing, I don't know. But thank you so much for being here. So thank you.